Okay, so welcome to the lecture 43. So this is 42 lecture we have completed. So now this is 43, and we will continue with the canonical transformation. Formation. So in last lecture we have seen that a generating functional of this form qi qit can generate canonical transformation provided that this function satisfied pi equal to del f1 del qi and minus pi will be del f1 del qi. So, f1 is function of qi and pi, and the new Hamiltonian and the old Hamiltonian will be related by k is the new Hamiltonian, which qi pi the variables, new variables, canonical variables, with h which is qi pi and t plus del f1 del t. Okay. So, this transformation will be canonical transformation. This can generate a canonical transformation if it satisfy this condition. Rather, I will say that this function can generate a transformation through this equation which does not affect the dynamics, because we have started with the Lagrangian L and L prime plus df dt. So, this is the guiding equation which does not affect the dynamics. So, from here in the Hamiltonian formulation, so we write corresponding Hamiltonian for L, write Hamiltonian for L prime, and then we found that this condition will be satisfied if by a generating functional, which is called, this is a generating functional through this. So, we can say that the canonical equation of motion will be preserved if we have a f1 which satisfies this, or which generate transformation between the canonical variables with a small old set of canonical variables and the new set of canonical variables through this relation, then we will have the unaffected. And then we consider that one example, that how it can generate transformation, that generate transformation, how it can help. To illustrate that, we consider one example of generating functional. So, let us start with that. We could not finish in last lecture. So, f we started with m omega square q square cot q, and then so this will generate the transformation through this equation pi. So, let me write p, only one variable, so we do not need any index. So, p will be del f1 del q. So, it will be m omega square q cot q, right. Okay. And p will be minus half m omega square q square minus cosec square q, right, because I have to differentiate cot q. Cot q differentiation is cosec q and minus sign from the formula. So, from here if we find, if re-express the second equation in terms of small q, then it will be 2p by m omega square root sin q. Okay. Now, suppose we substitute this. So, this is a canonical transformation. So, our claim is that this is a canonical transformation because I have used those equation, right, from f1. So, this transformation will be canonical equation, and we will apply this to a harmonic oscillator. Simple harmonic oscillator will be p square by 2m equal plus half m omega square q square, suppose, and I will apply, will convert. So, this is my h. So, I will write in terms of new variables. So, k will be just you substitute this variable. So, P is your m square omega to the power 4 q square divided by 2 m cot square q, and okay. So, also we will set before we going to use, we also simplify P equal to m omega square cot q, but substitute the q. Q is root 2 p m omega square sin q. So, this will be cot q and sin q will be cos q, and 1 omega will get cancelled. So, it will be, let me write, P will be 2 m p omega. Okay. So, 2 p m omega cos q. Okay. So, this P after substituting the q, so this is my P. Okay. So, that is why in last class we missed this step. Okay. So, now in so let me write my new Hamiltonian. P square will be 2 m p omega and cos square q by 2 m. So, this 2 m get cancelled, and then half m omega square q square will be 2 p m omega square sin square q. Okay. So, here we will cancel this 2 with this, m with this, omega square m, so half m omega square q square. So, this q will be just a moment, this there is a typo also, let me, this P this is fine, this has this q root 2 omega, just let me figure out where is the typo. Actually the choice of this F1, there was a typo. So, that is why I am not getting this. This actually this will be only omega, not omega square. So, this is omega. So, let me correct this with red pen. So, this will be only omega, this will be only omega, and then this will be only omega. Okay. And fine, and this also P small p will be m, this will be only omega, and here it is omega, here also will be omega. So, there will not be so there will be omega. Okay. So, I while writing the F1, I took by mistake omega square. That is why I was in last class also, I was not getting the correct factors, but anyhow. So, now we have find it out. Okay. So, if I substitute this in the expression for simple harmonic oscillator, so it will be p square by 2 m plus half m. Here we have omega square. So, that is why I took this mistake. Okay. So, now p square will be 2 m p omega by 2 m plus half m omega square q square will be, q square will be q is 2 p m omega, 2 p m omega, and this is cos square q, and this is sin square q. Okay. So, if you have, then you will find P see here m get cancelled, 1 omega get cancelled, 2 get cancelled, so p omega from sin square q. Here 2m get cancelled, p omega cos square q. So your new Hamiltonian is very simplified, p of omega. So it does not depend on q. So q becomes cyclic. Now q is cyclic. So this is the motivation I told you in the beginning, that by means of some transformation you can make some coordinate cyclic, then your algebra to solve the procedure will drastically change, because for cyclic coordinate you will not have to, you will not get, you do not have to do the dynamics, you do not have to find this. So at this point what is the conclusion? That a transformation which is generated by our choice of F1 I wrote, which I did mistake also in writing F1, and q, p will be this and q will be this 2p m omega sin q. Okay. So F1 half m omega, now not omega square, half m omega q square cot q. This will generate this canonical transformation, which will reduce new Hamiltonian to your p omega. So q cyclic. So this will helpful, and I will see how the solution can be found. Okay. So your k equal to q is cyclic, so q dot, so p dot will be 0 del h del q, but q is cyclic, so this is 0. So p will be say some variable, and this p is nothing but your k by omega. So this is constant, right. K is now the total energy, so this we can write E by total energy is constant. So this is E by omega, which is constant. Okay. Now let us find q dot. Now q dot is del h del p is omega, because h, the new Hamiltonian, sorry, this will be k. The new Hamiltonian is depends on, new Hamiltonian is p omega. Okay. So if it is p omega, then it is just omega and q solution, and omega is constant, so q will be omega t plus say alpha. Okay. So q changes linearly. Okay. Now we have to invert back to our original coordinates. For example, q we have to find. So let us see our q, that original variables was 2p m omega sin q. Okay. So now p is E by omega, so 2e m omega square, I substitute p by this relation. Okay. And sin q, q is omega t plus alpha. So this is your solution, and that is our known solution for simple harmonic oscillator. So what we have done, so let me summarize this, that suppose where canonical transformation will be useful, where it may have application. Suppose you have a Hamiltonian H, say in terms of old variables q and small q and small p, and the canonical equation canonical equations are difficult to solve, or this is a complicated Hamiltonian which you cannot solve, but you have to find to the solution of the system. Okay. So if you want to go to the solution of the system, but you cannot go this direct procedure process, because canonical equation are difficult or complicated to solve. So what you can do, we can make a canonical transformation you can make a canonical transformation to go to a new Hamiltonian, which is in terms of new canonical variables, so which may be simple. Now this Hamiltonian is simple Hamiltonian. Then simple means its canonical equations are simple, we can easily solve. Okay. Now what happened? Now if you can find a solution, you find a solution. So solution in terms of Q. Okay. But you need to find a solution in terms of small q, not the capital Q. So you follow the inverse canonical transformation to go to this solution. So canonical transformation will have application if this happens, that going directly from Hamiltonian to the solution may be difficult. So what we do, we follow a longer route but simpler. We use a canonical transformation to simplify the Hamiltonian, then the equations are simple, maybe some coordinates are cyclic in new Hamiltonian, and then we find the solution which easily, and then we use the inverse canonical transformation to find the solution. So canonical transformation, using canonical transformation, this method, route will be easier, and then we will have a real application of canonical transformation. Okay. Okay, so this is the so far we know that generating functional which can generate, and then we can but how we'll check directly a transformation is given, how we check directly whether this transformation is canonical or not. So for that we need some condition. So condition to check whether a transformation is canonical or not. Okay. So this can be found, see when we find in the Lagrangian formulation the equation of motion. To find this in the Lagrangian formulation, particularly in the Hamilton's principle, we consider the action to be the delta S to be 0 between the initial and final point. So L dt should be 0. But we have to, for canonical transformation, we have to consider this variation in terms of Hamiltonian. So the variation delta between this 1 and 2 point, you will consider that pi qi dot minus L, and if the system is canonical, not L, this should be H, we should be careful, and should be 0 for equation of motion, that we know action, it should be equal to the initial and final time sum over pi qi dot minus k. This condition has to be hold for a canonical transformation. Okay. So if I rearrange bringing these two, we can have a delta, then we have integration 1 to 2, we have sum over pi dqi minus pi dqi, these two terms we combine together, sum over I equal to 1 to this, and plus we have k minus, I bring this, so k minus h dt. So this has to be 0, right? I am just equating those two, so this has to be 0. So its transformation has to be canonical. Now we, from here the variation will be 0, that we know from our Lagrangian formulation, that if this quantity becomes a total time derivative or total time differentiation, then we can say that this will be 0, variation will be 0. So we can say from here that's pi dqi minus pi dqi, sum both places, sum over here to here, plus h prime minus h dt, if it is exact differentiation, the whole integrand, if it is exact differentiation, say f1 of some exact differentiation function, then we call that this equation will hold and that transformation will be canonical. And from this condition we find that your h prime minus h will be del f1 del t, and your del f1 del qi will be pi, and del f del qi will be minus pi. So this is the same condition, same I'm sorry, h prime we have not written, h prime का जगह हम लोग in h prime we are writing k, okay. So this will be k minus h. So this also, make this correction, this will be k minus h. K is our new Hamiltonian. Sometimes some people also use h prime, so that is why I did mistake. Okay, so your new Hamiltonian k will be old Hamiltonian plus del f del t, okay, if it is time dependent, and these are the, this f1 is the generating functional, so these are the canonical transformation, okay. So what we obtain, that for when f doesn't depend, on time, your k will be h, that means k in q I pi will be h q I pi, okay. And you will find that your sum over pi dqi minus capital Pi dqi, this quantity will be exact differential. So a transformation to be canonical, that we find for this, when generating functional does not depend on time, you will find that this has to be the exact differentiation. So let us use this concept for an example to understand this. So let us, a transformation given. So example, a transformation is given, capital P is half p square plus q square, and capital Q equal to tan inverse q by p, okay. So this is canonical, so we have to check whether this is canonical or not by this differentiate method. So only one variable, one coordinate, one momenta, so we will not have a summation. So what we have to show, p dq minus capital P capital dq should be exact differential. That means it should be d of some quantity like this, exact differentiation. So let us calculate this for this transformation, very simple example. So dq, p dq I will keep as it is, and then capital P I will write in terms of old variables, p square plus q square, and dq tan inverse derivative. So, tan inverse derivative is 1 over q square plus q square by p square, and then differentiation of this, which will be dq by p minus q p square dp, right. Okay. So, this is the differentiation of tan inverse q by p. Okay. So, now let us simplify this. So, p dq minus half p square q square, and if I take the p upside, it will be p square plus q square into dq by p minus q p square dp. Okay. So, you can see this will get cancelled with this. So, p dq, then half p square, if we multiply by p square. So, first term will be p dq, second term will be minus q dp. Okay. So, we will have p dq minus half p dq plus half q dp. So, this, if we combine these two, it will be half d of qp. So, d of half qp. So, it is the exact differentiation. So, if it is exact differentiation, we can say that this implies that transformation p equal to half small p square plus small q square, and q tan inverse q by p, this will be canonical. Okay. So, with the simple, so we find the condition for canonical transformation and we verify for a simple example. Okay. So, now so far, so let me summarize what we have learned. So, we have seen the point transformation, and we find that to generating functional for that functional. Then we motivate for canonical transformation. This generating point transformation you can consider in the Lagrangian formulation, and then we motivate for canonical transformation, that if we make transformation and to simplify the dynamics to find solution, particularly the example of that if we make transformation and find some coordinate cyclic, then it will be helpful. Then we find that a function f1 q and t, how it can generate the canonical transformation. So, canonical transformation when del f1 del q is p or many variables. So, let us put I, and then del f1 del capital Qi will be minus pi, and new Hamiltonian k will be h plus old Hamiltonian plus del f del t. Okay. So, this f1 can generate the canonical transformation. Then we find that what will be the condition, and we find that p dq pi dqi sum over I plus capital Pi capital dqi, this is exact differentiation, particularly when your generating functional does not depend on time, then it will be canonical. So, we have learned the condition for canonical transformation, generating functional for canonical transformation. Now, in next lecture will find that whether f1 is the only type of generating functional or we can have many generating functional. So, that we will concentrate in next class. Also we will consider that how the Poisson brackets will be useful in learning canonical transformation. So, bye for now. So, in next lecture we will consider the other form of generating functionals.